Elsa?
All right, so I'm going to go through and explain a slightly more challenging problem with respect to determining the order for a reaction. And it's more challenging simply because normally when we're finding the order for one reactant, let's say for A, we can find experiments where B and C will stay the same, or if we're determining the order for B, A and C will stay the same. And in this problem, that doesn't happen the entire time, so that's why it's slightly more tricky. Also, the numbers aren't as pretty as we normally see. So let's go through this one. So to determine the order of A, I'm going to look at experiment 1 and 2, because going from experiment 1 to 2, my concentration of A doubles, while the concentration of B and the concentration of C stay the same. Going from experiment 1 to experiment 2 here, my rate also doubles. And so if we write this the way we've done it before, if my concentration of A doubles, what would the order be if the rate also doubles? And the answer to that is that it would be first order. So we know that A is first order. Okay, not too bad. All right, let's now determine the order for B. So for this one, I'm going to go from experiment 1 to experiment 3. All right, and from experiment 1 to experiment 3. And the reason why I'm doing that is because my concentration of A stays the same, my concentration of C stays the same, so I can actually calculate how the change in concentration of B will affect my rate. So if I take 3.02 times 10 to the negative third and I divide it by 1.25 times 10 to the negative third, what I get is not a nice pretty number like we're used to. It's not a whole number, but that's okay. I get 2.416. Okay, and so I'm going to raise that concentration change by the order of the reaction, which I don't know, so I'm going to make it Y. And then I want to know how my rate changes. So I'm going to take 0.0508 and divide it by 0.0087. And what I end up getting, again, is not a perfectly nice, pretty number, but that's okay, 5.84. And so what I need to do is say, okay, 2.416 raised to the what equals 5.84. And when you actually plug that into your calculator, what you will find is that the order for this reaction is 2. So I have now determined the order for A and for B. It's first order for A and second order for B. So if I were to write out my rate law at this point, my rate equals my rate constant, my K, times my concentration of A, and it's just going to be A because it's first order, times my concentration of B. That's going to be squared because it's second order, times my concentration of C raised to the, I'm going to create a new letter, let's say T, okay, because why not? All right, so I still need to determine the order for C. So what I would love to do is find 2 experiments where the concentration of A and the concentration of B stay the same, but C changes. And unfortunately, the reason why this is a hard problem, I can't find that. That doesn't exist here. So what's going to have to happen is that either A and or B will also be changing while C is changing. I would love for just one of these to be changing so I don't have to deal with all of the math, but you could have all 3 changing and still calculate it, because ultimately, since we know the rate change, we know the change in A, change in B, I know the change in C, I can determine the order, I can determine my T. But to make my life easier, what I'm going to do is I'm going to actually just compare experiment 1 and experiment 4, because notice from 1 to 4, the concentration of A does not change, so I can simply ignore it here. From 1 to 4, my concentration of B does change, and from 1 to 4, my concentration of C does change as well. And so I'm going to plug in my values to be able to determine the order for C. So going from experiment 1 to experiment 4, if I took 1.828 and divided it by 0.0087, what you get for the change in rate, it increases by a factor of 210. All right? Then my concentration of B, going from 1.25 times 10 to the negative third to 6.04 times 10 to the negative third, that is increasing by a factor of 4.832. So not a pretty number, but that is okay. Okay, and it's second order here. Now I didn't include A, remember, because it doesn't actually change. So A is not going to affect the rate at all. So 4.832 is the change in concentration of B. I'm going to square that. Times, well, how is my concentration of C changing? Well, it's going from 1.25 times 10 to the negative third to 3.75 times 10 to the negative third. So it is tripling here. So what I need to do now is I'm going to take 210 and I'm going to divide it by 4.832 squared. And what I get is actually 9. And that actually looks quite nice because I got like 8.999. So what I'm now going to ask, and this now looks just like what we were doing over here, is say, okay, 3 raised to the what equals 9? The answer to that is 2. All right, so my order for C is actually going to be second order. And so I'm not going to answer the rest of these questions because you guys can do that and will, but my rate law here is simply going to be my rate constant times the concentration of A, and it's not going to be raised to anything because it's first order, times the concentration of B, and I am going to square that one because it's second order, times the concentration of C, and I'm going to square that one. And that's all there is to it. So unlike these two, where it was super easy to do because for this one, for A, the concentration of B and C stayed the same. For this one, the concentration of A and C stayed the same. It is still possible to determine the order for C, for example, even if the concentration of B is changing.